When we are trying to describe, or maybe better explain, why a reaction may go fast or slow relative to another reaction, we use the collision model or collision theory. The collision theory is very simple. It says that in order for two chemicals to react, they have to collide. They have to collide with the correct orientation, which has to do with, if I move myself here, the right atoms hitting the right other atoms to make the products we want. So in this case right here, we need the NO to hit one of the O's that is on the end of our ozone. When it hits the middle one, in that case or in that case, they bounce off unreacted, and it's an ineffective collision. So they have to collide. They have to collide with the correct orientation, and they have to collide with enough energy. So those two factors are very important. The energy is important because as these collide, whether they're correct or incorrect, we also have to account for the fact that we are breaking a bond within a molecule, which requires energy. We are making a bond in another molecule, which releases energy. And it's those bond breaking and bond making events that actually turn reactants into products. Only when we can collide in the way that allows for that do we call a collision successful. And an important piece is that in most reactions, we'll have not just a few, not just a few dozen or a few hundred, we have more than trillions of molecules. And as they bounce into each other very much, sometimes quickly, sometimes slowly, we actually don't have very many collisions at any instant that are successful. But the more successful collisions we have per unit time, the faster the rate. One of the things that connects with that, whether the collision is successful or not, is what's called the activation energy. It's represented in these two graphs in two slightly different ways. When we look at potential energy, we can see that our reactants could be graphed with a certain amount of energy and our products with a different amount. We will talk about endo and exothermic reactions and describe them based upon where our reactants are starting or ending. But regardless of that, there is an energy barrier or a hill that we have to overcome. That is the energy needed to collide those two molecules so that they break and make the bonds and actually turn into products. It's represented a little bit different here. This is a Maxwell Boltzmann distribution. It shows us what fraction of our molecules have a certain energy. And as odd as it may seem upon first look, the shorter, flatter curve is actually representing molecules moving faster. Even though it's not as tall, as it's shifted to the right, that's showing us that we have more molecules with a higher kinetic energy. The kind of skinnier, taller graph shows we still have the same total molecules, but a higher percentage of them have this lower kinetic energy. In both cases, the area under the curve is what's representing our total number of molecules. Whether it's an uphill struggle or whether it's looking left to right here at how many of our particles are moving really fast, there is a barrier, or a minimum energy needed to react. It's the activation energy, or we would label and simplify that as E sub A. We sometimes think of it as the transition from kinetic to potential energy, but in either case, it is the energy that the molecules possess. And we'll see later that during that process, during an effective collision, we not only have we don't have our reactants nor our products, but we're in a transitional state that's sometimes called an activated complex. The value in the collision model is it allows us to see how we could make a reaction faster. And with this model and theory, most of the changes that we can make have obvious, easy to understand, and easy to explain outcomes. One main factor relates directly with the energy that the particles have. It is the temperature. At a higher temperature, reactions will occur more quickly. That's because the molecules, the atoms, particles, molecules, and ions move faster. They collide more frequently when they're moving faster. They collide with more energy when they're moving faster. And those more energetic collisions and more frequent collisions are more likely to be successful. More of the atoms have the minimum activation energy to get over the barrier, and they are colliding more often. So our fast particles will collide faster than our slow. We can also change the concentration. Concentration is the main factor we're looking at in measuring the reaction rate over time. But if we wanted it to be consumed faster, we could impact the concentration ourselves. Putting a higher concentration in increases the rate. This would be a high concentration, a lot of particles per unit volume, versus a low concentration. When we have a higher concentration, more molecules are present. Those particles end up colliding more frequently with one another, and those more frequent collisions are more likely to lead to a successful collision. With more collisions, the orientation of a few of them is more likely to be right. We can also, if we're dealing with a solid, break it into smaller pieces by impacting its surface area. Breaking a big chunk into smaller pieces increases the surface area and increases the rate of reaction. More of the molecules are exposed to one another in that case. Here we actually have more molecules. Here we have the same amount, but more exposure between them. More frequent collisions would come along with that, and once again lead to more successful collisions. One thing that we can do that in some ways doesn't seem fair is kind of change what our reactants are. Some things react faster than other things. So if we want to understand why something's fast or slow compared to another, with other factors being similar, concentration, surface area, or temperature, we can understand the reactants themselves. We can swap something out if we want it to go faster. Strong versus weak electrolytes has to do with how broken apart the molecules are and likely how available they are to collide. So strong acids often react faster than weak. Things with strong bonds are harder to break apart. They have a higher activation energy and are much less likely with the same force of collision to react. Our solids not only are moving more slowly than liquids or gases in general, they also may have a different amount of surface area. So gaseous molecules tend to be the fastest to react. And then as we look at different molecule sizes, complex large molecules won't react as fast as the small ones for restrictions of surface area, but also how fast the particles can react. Also, if there's just one specific spot on a molecule where the reaction may occur, the chance of that collision happening successfully with the right orientation is very low. So all of these lead to more frequent collisions, which happen to be more successful. As we talk about rate, we'll talk several times about what catalysts do. But a catalyst is defined as a chemical that speeds up the reaction, and they do so not by making it hotter, not by putting more particles in or changing how they're arranged, but by creating a new pathway, maybe some new bonds that need to be broken or formed throughout the process. That new pathway somehow has a lower activation energy. A big mistake we're going to avoid is to say that heat is a catalyst or that catalyst heats it up. Those are two different factors. The speed of the particles versus a new different chemical changing the pathway of the reaction. But we've got these factors that all come back to understanding how hard and how they're oriented when molecules are hitting one another.